Now up till now we have studied Grignard reagent. We have seen one small conversion concerning Grignard reagent, and we have seen most of the reactions. We have seen almost all the reactions of Grignard reagent, and we have seen one of the reaction of Grignard reagent when it attacks carbonyl group. Now this thing we understand now quite well, that this Grignard reagent has negative charge on carbon, so this will attack the carbon of carbonyl group, because the carbon of carbonyl group is electron deficient because of the shifting of electronic density of this C double bond O towards oxygen, because of greater electronegativity difference between carbon and oxygen. Now similarly, suppose we have carbon dioxide gas. In carbon dioxide gas we have 2 C double bond O, and the deficiency of electron on the carbon in carbon dioxide gas is much greater than what it is in carbonyl group. So because there are 2 C double bonds O and electrons will be pulled by oxygen on both the sides of carbon, so the deficiency will be cumulative effect of these two, and the deficiency will be greater. So somehow if I made this Grignard reagent and this carbon dioxide gas to react by adding carbon dioxide gas in a high pressure, or by adding dry ice into the system having Grignard reagent, then this Grignard reagent will come and attack this carbon. The pi bonds will shift onto the oxygen, and we will have carboxylate ion. Now this carboxylate ion on subsequent protonation will result as a carboxylic acid. This becomes an important method of preparation of carboxylic acid, which we will again see in the chapter carboxylic acid. So this is the reaction that we must be aware of, and I'll use this reaction in the conversions that subsequently we are going to do. So when Grignard reagent reacts with carbonyl compound, it produces carboxylate. When Grignard reagent reacts with carbon dioxide gas, it produces carboxylate ion, and on subsequent protonation we have carboxylic acid. Now at this juncture I would like to tell you a reaction that a reagent that is quite similar to Grignard reagent, but it differs much in the reactivity with the Grignard reagent. In Grignard reagent we have RMgX, negative charge on R, and we have magnesium ion as a central ion. Now this is dialkyl cadmium. In dialkyl cadmium will also have negative charge on R, but here the central metal ion will be cadmium. In case of Grignard reagent we have magnesium. So chemically both are comprised of the reactive part, that is R minus, but the difference in reactivity will be much, because here we have magnesium ion. This magnesium ion is a S block element. Magnesium is a S block metal. Here we have cadmium. Cadmium is a D block metal. Magnesium belong to third period, cadmium belong to fifth period. In magnesium we don't have d orbitals. In cadmium we do have d orbitals. In magnesium shielding effect is more. In cadmium shielding effect is less. So what happens is, in magnesium ion internally you have a nucleus that has some positive charge, and when you have some electron outside, this nucleus attracts those electrons. Same would be the case with cadmium. In cadmium you'll have a bigger nucleus because of greater atomic size. You'll also have distance from the nucleus larger because the shell number will be higher than that in case of magnesium. So if you have some external electron, and these electrons I'm talking about are the electrons of this R, so they are not in the shell of cadmium, they are not in the shell of magnesium, but they are outside. But still this nucleus will have some influence on these electrons, and this nucleus will tend to attract these electrons. Same will be the case with magnesium. But in case of cadmium, there is more shielding effect. Now this shielding effect term you must have heard in the chapter periodic table, or in case you haven't heard yet, you will study in the chapter periodic table. Shielding effect means that, suppose this is an internal shell between the outer shell and the nucleus, and there are some electrons in between. Now these electrons will try to shield the effect of this nucleus to the outer electron. This effect is called shielding effect. If you have some electrons in between, these electrons will tend to repel the electrons which are in the outer shell or outside the outermost shell. So it will act as a barrier between the internal nucleus and the outermost electron. Now this effect is called shielding effect. Now since the electrons, most of the electrons in cadmium is in d orbital, so d orbital, as we know, it is a bigger orbital, it is more diffused than s and p. So this shielding effect, because electrons are more diffused, so they cover more of the space around. I mean, here we are looking at the Bohr model. I have drawn orbits, but after studying atomic structure, we do understand that electrons are not like particles revolving in an orbit. They are diffused in space, and when the orbital is bigger, that diffusion is greater, and the shielding effect becomes less pronounced. So what happens is, nucleus has greater access, have a greater influence on the outermost electron. So this nucleus will attract the outermost electron more strongly than what this nucleus does. So due to shielding effect, lesser shielding effect of electron, the outermost electron is not shielded with the nucleus. So they are more attracted to the nucleus. So this cadmium plus 2 ion will attract the negative charge of this R minus more strongly, much more strongly than what this magnesium ion does. So this R minus in case of dialkyl cadmium is more tightly held than what this R minus in case of magnesium plus 2 ion is held. So this R minus tends to get stabilized because of stronger electrostatic force of attraction. There will be kind of ionic bonding because both are ions, and here that kind of ionic bonding will be very less because the attractive force with magnesium will be less. So that becomes the reason why this dialkyl cadmium is less reactive than Grignard reagent, because in dialkyl cadmium the nucleus of the metal, that is cadmium, offers more attraction to the negative charge of the alkyl group, and that tends to stabilize it. So these electrons are more tightly held with the cadmium, so they are less free to get poured into the orbital of some other atom. So this becomes less reactive, this becomes more inert towards pouring its electron into someone else's orbital. And by now it's very clear to all of us that reactions are nothing but transfer of electron from one orbital to another, and the electrons are very tightly held in one's orbital. They will have less tendency to get transferred to someone else's orbital, so that will make it less reactive. So the bottom line of whole discussion is dialkyl cadmium is much less reactive than Grignard reagent. This intuitively we can understand. Same would be the case if instead of Grignard reagent, instead of magnesium plus 2 ion, I take copper plus 2 ion. If I have Cu plus 2 ion and R minus is somehow bonded with this Cu plus 2 ion, although it's not a complete ionic bond, but still this is some kind of electrostatic force of attraction between this R minus and Cu plus 2, and this electrostatic force of attraction is greater than what magnesium offers. So Cu plus 2 will have same kind of reactivity as Cd plus 2. So both the alkyl group, if they are attached with divalent metals of D block, they will be less reactive. If they are attached with divalent metals of S block, they will be more reactive. This you must understand. And what is the parameter of this less reactive and more reactive? This we are going to understand, and you have to bear this in mind towards the end of the syllabus. You have to understand it because this thing will be again repeated in all the chapters that we are subsequently going to start. Now the difference in reactivity that we are talking about is this. Suppose I take acyl chloride. Now this acyl chloride is most reactive of all the acid derivatives as we have seen, because the bond of this the electrons of this bond are shifting towards oxygen, and the electrons of this bond is also shifting towards oxygen, as we have also shifting towards chlorine, as we have seen many a times before. Because chlorine being halogen, and in case of halogen we know that the inductive effect dominates over mesomeric effect, so it will pull up more of the electron via inductive effect than what it does, than what it gives through plus M effect. So there are two electron withdrawing groups attached with carbon, so the electron deficiency on this carbon is quite high. So in this case, when there's a large amount of deficiency on carbon, both dialkyl cadmium and Grignard reagent are able to react with this acyl chloride. So whether you add Grignard reagent or you add alkyl cadmium to this acyl chloride, you will have ketone. This we have seen many times how we'll get this. Actually this R minus will go and attack the carbonyl group, and to facilitate the regeneration of C double bond O, the Cl minus have to be removed off. So the Cl minus will come out of the substrate and a ketone formation will be there. This we have already seen. Now the difference comes here when it becomes a ketone. Now in this ketone, instead of chlorine you have R group. Here chlorine was electron withdrawing the electron. Here R group will be pumping in the electron. R group will be giving electron to this electron deficient carbon. So in here chlorine was increasing electron deficiency. Here R is decreasing electron deficiency. So the electron deficiency of the carbon in carbonyl group of ketone is less than the electron deficiency of this carbon in acyl chloride. So this carbon becomes less reactive than this carbon. So the difference in reactivity is such that Grignard reagent will be able to react with this carbon. Dialkyl cadmium will not be able to react with this carbon. This you have to bear in mind. The reactivity difference of Grignard reagent and dialkyl cadmium is such that dialkyl cadmium will not be able to react with ketonic or aldehydic group. Dialkyl cadmium will not be able to react with carbonyl groups. Grignard reagent definitely will be able to react. Now if we have acyl chloride, then both will be able to react. So this carbonyl compound, this ketone and this aldehyde becomes the parameter. With aldehyde ketones, all those compounds which will be more reactive than aldehyde and ketones, dialkyl cadmium will be able to react. All those compounds which are equally reactive to aldehyde and ketones and are less reactive than aldehydes and ketones, this dialkyl cadmium will not be able to react with them, because the reactivity of both substrate and reagent, if that is less, there is no reaction. As you have seen in your previous early classes at school level, that if you have a strong acid and you have a weak base, then this is a reaction. But if you have a weak acid and you have a weak base, then the reaction extent is very less. So similarly, if you have a strong substrate and if you have a strong reagent, then definitely reaction will take place. But if you have a strong substrate and even if you don't have a strong reagent, still reaction will take place, because here this acyl chloride is a strong substrate, because it is this is unstable, this is very reactive. And even if you have a less reactive reagent like dialkyl cadmium, still reaction occurs and you will have a ketone. But once you have a ketone, the substrate is also less reactive and the reagent is also less reactive. In that case, you don't have any reaction. So this you have to remember. Ketone and compounds less stable than ketone will not react with dialkyl cadmium or Gilman's reagent, where you have copper +2 ion instead of cadmium +2. And with Grignard reagent, of course, all of them will react, because Grignard reagent is very reactive because it's very unstable.